With the homework, I said that you were ready to work on problems like something through 8, I think, but yeah, 2 of those though are free fall problems. So so we haven't talked about that yet. We'll talk about it today. So I shouldn't have assigned those. You might have been. I mean, mathematically, maybe you could sort of figure out how to do it, possibly, but it'll make a lot more sense after today. So sorry about that. Anybody have any homework questions besides those 2? We do? Were we in the middle of one? Oh, really? Was it the ball in the ramp? Oh, okay. Yes, I remember shooting him. He's still up there. We got to get him down. Let's see. How long does it take? Okay. Yes. So Cannonball Man continued. So after the first part, here's what we know and what we want. We know that the starting position, P sub I is 0. The final position is positive 3 meters. The initial velocity is 0. The final velocity is 12 meters per second. And now we calculated the acceleration, which is 24 meters per second squared. And we're trying to find time final. So is there an equation that has time final in it and everything else that's in it is known? The first one, yeah. If you ever can use the first one, like there are a lot of cases where you can use more than one, use the first one if you can because it's the simplest. Especially if you're solving for time, because you could also use that second equation, but look at that second equation. Look at how time appears. You know what you have to use to solve something like that usually? Quadratic formula. And no one likes that. Okay, so let's use V final is equal to V initial plus A times time final. So 12 meters per second is equal to 0 plus 24 meters per second squared times time final. And so I'm switching everything over to the opposite side. Time final is equal to 12 meters per second divided by 24 meters per second squared. Okay, so I'm going to set that up as 12 meters per second is 12 times meters divided by seconds. And to divide by 24 meters per second squared, we're going to switch everything in the numerator to the denominator and everything in the denominator to the numerator. We're taking the reciprocal of it. So 24 meters and then seconds times seconds in the numerator. Any questions about that step? So the cancellations, you lose the meters, you lose one of the seconds, and the units come out what we'd expect for time. They come out to be seconds, and we get a total time of half a second. Any questions about that? You want to work on one? Ready to work on one together? Yes. You've been doing the homework anyways. Yeah, you're ready. I know you're ready. Don't be nervous. A car hits the brakes and slows down with an acceleration magnitude, so this can be plus or minus, of 8 meters per second squared. If it takes 3 seconds for the car to stop, how fast was the car going to start with? Okay, so let's take a few minutes, see if you can work your way through this problem. I would recommend being very careful for now about going through the steps, go through it step by step. Eventually that stuff will kind of become ingrained and you won't have to worry about it as much. But for now, step 1 is you make those choices. Step 2, list out what you know and what you want. Step 3, look for the equation, okay? And as you go, talk to each other, compare where you are at each step with each other, laugh together, cry together. And then if you and the people you're working with are all stuck, feel free to ask me questions and I can help you. But after you're done, after we work on it for a while, I'll go through it up here too, okay? Okay, so I'm going to start by just drawing what's happening. This is how you draw a car that is slamming on the brakes, according to because the wheels are backwards or tilted backwards, you can see it slamming on the brakes. You can also write screech. Okay, so the car is going this way, and here's where it stops. We don't know what that distance is. So step 1, we have to make those 4 choices. An instant corresponding to time equals 0, and an instant corresponding to time final. And then we have to choose a position equals 0 and a positive direction. Time equals 0 and time final. We decide that based on where we know stuff and where we want to find stuff. So we know that over the whole thing, acceleration is constant. So acceleration holds over the whole thing. So that doesn't help. We know that it takes 3 seconds to go from where it slams on the brakes to where it stops. So that's information that deals with both of those two instants. So the first bit of information suggests time equals 0 here and time final here. Then we want to find a velocity where it slams on the brakes. So that's something we want that's at that left mark. And then we know the velocity when it stops is 0. So all of that points to the same choices for time equals 0 and time final. We want this to be time equals 0 and this to be time final. Why not make this time final and this time equals 0? Because we don't have negative times, you know. So time equals 0 always has to be the earlier time, the earlier instant. So time equals 0 is when the car hits the brakes. Time final is when it stops. And now position equals 0. I said last time that sort of my default choice is to make the position equals 0 at the location, at the thing's location when time is 0. So that means I'm going to make this the position equals 0. And I might as well put the positive direction in the direction of motion. So position equals 0 is at the car's location at time equals 0, and the positive direction is the direction of motion. Okay, so now we have to think about what we know and what we want. And I'll go through these in order. Do we know the elapsed time between 0 and time final? 3 seconds, yep. So time final is 3 seconds. Do we know the position when time is equal to 0? Anytime we make our choice this way, where is it? So anytime we choose our position equals 0 to be the object's location when time is equal to 0, that's just like another wording of saying P initial is equal to 0. Okay, that's saying at time equals 0, the car's location is 0. Okay, that's sort of an easy one to work with if you don't have a reason to choose anything else. So P sub I is equal to 0. Do we know position final? No, we don't know how far apart they are. Do we want to know that? No, we're not asked for it, so if we can get away without it, that's no problem. Do we know the initial velocity? That's the velocity at time equals 0. Do we care about that? That's the thing we're looking for, yeah. Do we know the final velocity? Yep, it's at rest. And then the last one is, do we know the acceleration? Okay, this one is tricky here. So we don't know what the velocity is when it starts, but which way is it moving? It's moving in the positive direction. Is it speeding up or slowing down? It's slowing down, and so is the acceleration positive or negative? The acceleration has to be negative. So acceleration here is negative, what did I say, 8? 8 meters per second squared. Okay, and now is there an equation that works with these? Yeah, the simplest one. V final is equal to V initial plus A times time final. So it says 0 is equal to V initial minus 8 meters per second squared times 3 seconds. And so I can rearrange that to say V initial is equal to 24 meters per second. Oh, that's all I had to do here. Anybody want me to elaborate on that multiplication at all? We have seconds in the numerator here, seconds squared in the denominator, so it just cancels one of those in the denominator. Does it make sense that the initial velocity is positive? Yep, that's the way I drew it, so that makes sense. And it's the opposite direction of the acceleration, which means it's slowing down. Let's answer one more question about this. What's the displacement between when the car hits the brakes and stops? So first of all, what's displacement? That's an important thing to know before you can answer this question. Displacement is the later position minus the earlier position. So in this case, displacement is going to be position final minus position initial. Okay? So in order to find displacement, what we need to figure out is the final position. That's the only thing we don't know. So let's list out what we know and what we want. Do we know time final? Yep. Always knew that. Yes. Great start. Do we know initial position? Yep. That's 0. T final is what we're looking for. Do we know initial velocity? Now we do. I don't remember what it's, 24. Initial velocity is positive 24 meters per second. Do we know final velocity? Yep, comes to rest, so that's 0. And then do we know the acceleration? Yep, that's negative 8 meters per second squared. Okay, so is there an equation that works with those? The second one, I think. The last one will work too, I guess. So let's use this second one that says P final is equal to P initial plus V initial times time final plus 1/2 times acceleration times time final squared. So P final is equal to 0 plus 24 meters per second times 3 seconds plus 1/2 times 8 meters per second squared times 3 seconds squared. So I'll do these two separately. The orange dot there yes, thank you. Thank you. So 24 meters per second times 3 seconds. I'll write that as 24 meters over seconds times 3 seconds. The seconds cancel, and we get units of meters, which is good because we want our final position to be in meters. So that's 72 meters. And then the second piece, I'll call that one the green dot. That's 1/2 and then times -8 meters over seconds times seconds. And then times, we have to square the 3 and square the seconds, so that's 9 seconds times seconds. So all the seconds cancel, and we get negative 36 meters. And so add those up, and the final position is equal to 72 meters minus 36 meters, so 36 meters. That's the final position. It's the displacement is the final minus the initial. So displacement is 36 meters minus 0, which is 36 meters. Another thing that makes it sort of nice to choose your 0 position at the starting location. Any questions about that? Okay, so now we're going to talk about the one type of motion, the most important type of motion that that has constant acceleration, and that's free fall or projectile motion. And I think in everyday language, people think of those two things as being different. Free fall is just falling straight down, and projectile motion is if something's launched. But to us, this is interchangeable. They both mean the same thing. And what they mean is the only force acting on the object is gravity. Well, as long as we're on Earth, this never holds. So let's change this to say the only, in here I'll put significant. So the only significant force acting on the object is gravity, which means as long as air resistance isn't making too big of a difference on the object's motion, we'll consider it free fall. But what this means is, for sure, so look, okay, so this is an approximation. Anything moving on Earth is affected to some degree by air resistance. So when is it, so you can think of the free fall projectile motion calculation as being just an approximation. It's never true. It's always approximating motion. So when is it reasonable to make that free fall approximation? And the answer is, this part is non-negotiable. The object can't be touching anything. And the second requirement is that, yes? Yeah, well, on Earth, you know, you can get pretty close to complete vacuum, but there's actually always air particles in the vacuum. So yes, and I'm going to show a video of of a vacuum, that's pretty cool. But no matter where you are on Earth, even in the best vacuum, there's still air resistance. It's just a question of how much you're comfortable assuming isn't there, you know. So the second one is that the force applied by air resistance much smaller than the force applied by gravity. Okay, so I'm going to go through a list of the things that make this, make air resistance a significant contributor. You know, like for kind of intuition, you know, if I got this thing to the floor from here, assuming there's no air resistance would give us a really good approximation of its motion. We could do the calculation, it would match up almost perfectly with what we saw on a videotape. But think of another thing that has nothing touching it. It's just out there alone in the air, and that's like a helicopter hovering, you know? Well, free fall approximation is a terrible approximation of a helicopter, you know? Free fall approximation says a helicopter should just fall straight down to the ground. But helicopter is designed to maximize air resistance in a way that keeps it from falling, you know? So those are some of the, we're going to talk about what some of those distinctions are. But before I do that, I want to show this video and kind of clear up a very common misconception about the way gravity works. If air resistance is negligible, or maybe better, let's say, if air resistance has a negligible effect on an object's motion, all objects fall with the exact same acceleration, no matter how big they are, what their mass is, and even independent of how fast they're moving or anything like that. All objects have a downward acceleration of 9.81 meters per second squared. This is on Earth. And so this is an important misconception that a lot of people have. Common misconception. Gravity makes heavy things fall faster than lighter things. Some of the most important scientists in history still thought that this was true. And it wasn't until the 1700s that people realized this wasn't the case. It often happens that light things don't fall as fast as heavy things, but that's entirely because of air resistance. And if you remove air resistance and drop a piano and a feather, they'll fall exactly the same, and their acceleration will be exactly the same. So let's watch a video about that because it's cool. So what this video is it's a gigantic vacuum chamber where they're able to suck almost all the air out of this gigantic room. And once all the air is sucked out, there's virtually no air resistance on anything, and you can see just what gravity alone does when objects are in free fall. Okay. Who's excited? Yes. Who to the rest of you? Oh no, come on, sound.
NASA's space power facility near Cleveland.
That's coming through there, right?
And it is the world's biggest vacuum chamber. It's used to test spacecraft in conditions of outer space. And it does that by pumping out the 30 tons of air in this chamber until they're about 2 grams.
Oh, pause. So he's going to talk about that chamber a little, but what we're going to watch is first, up from the top, they're going to have a bowling ball and a feather. When that, oh, is it a vacuum yet or not? How do you know? Yeah, because he's not dying. Yeah, exactly. Right. And so before they suck the air out, they'll drop the bowling ball and feather at the same time, and just what you expect to happen will happen. The bowling ball will fall down fast, and the feather will drift down slowly. And then they'll suck out all the air and do the same experiment. And what you're going to see is a bowling ball and a feather falling that whole distance exactly next to each other. The feather is going to hit the bowling ball hits the ground and smashes into the whatever it lands on. The feather hits the ground and bounces. It looks like it's made out of, metal or something. It's just really cool. Okay, so here you go.
And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
Oops. I just trying to get rid of that. Yeah. Okay.
It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set by 240 psi. We are go for drop.
10, 9, 8,
7, 6, 5, 4, 2, 1, release.
They came down exactly the same. Wow.
Look how they hit that. Exactly the same. Exactly the same. Feathers don't move. Nothing. Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's
Okay, let's stop there.
pulling them down.
Yes. Yeah. Well, yeah. So I know that is funny, except like they were saying at the beginning, like this is for those people don't work here dropping balls and feathers. They work here testing aircraft equipment. So that is sort of funny. Like you've never done that before, but yeah. So even the fact that as you're watching the feathers go, they don't even whatever wobble. Because there's nothing to no wind or anything. If just a second, okay. In a lot of the moon landing hoax stuff is based on people's feelings about what's happening to the flag. I don't know. Have you ever heard about, like, there's all these people who don't think that there was ever a moon landing, and you know, there's this list of all this evidence, and a bunch of it is based on there's a flag in the ground, and like, for example, they say the flag is rippling, and they say, well, there's no wind, you know, the flag wouldn't ripple, but you know, wind is what makes a flag ripple usually, but it's also what stops a flag from moving. So if you hit a flag on the ground and it starts wobbling a little, eventually the air stops it, that air resistance. But if there's no air, it'll just keep doing that forever from you just banging it on the ground, you know. Yes. Yeah, they were showing it in slow motion. Did they ever show it full speed? Yeah, it falls, you know, they both fall at the exactly like the bowling ball would fall. Any other questions? Okay, so the point of that video is that for some reason, gravity, if it's the only thing acting on objects, no matter what the mass or shape of those objects are, they'll always accelerate down with the same acceleration. And any variation from that is just totally the result of air resistance. Okay? And so, for example, what that says is the more something deviates, when you drop something, the more it deviates from a downward acceleration of 9.81, the more air resistance affects its motion. For example, feathers that flutter around and fall really slowly are hugely affected by air resistance. A bowling ball isn't very much. So I want to go through just a list of the things that affect air resistance, and so that you can get a sense of what kind of objects you might want to approximate as free fall, and which ones it would be a bad approximation for. for example, feathers, we wouldn't almost, even if you drop a feather like an inch, free fall wouldn't be a very good approximation for a feather. It just catches too much air and it's too light, you know. Okay, so what are the things? So what affects air resistances, the influence of air resistance on an object's motion? What affects the influence of air resistance on an object's motion? Well, the first thing is the mass of the object. Increasing the mass of an object without changing the other things that we'll talk about. So increasing the mass causes air resistance to affect the motion less. An example of that is, so for example, imagine a bowling ball and a beach ball that's the same size. You know, they're both spheres with the, say they have the same diameter. Bowling ball has a lot more mass though, and if you drop both of them off a high enough roof, you know, drop it off a house, the bowling ball is going to hit the ground a lot sooner than the beach ball. By the way, what would happen if you dropped a beach ball and a bowling ball at the same time in a vacuum chamber? They would, but first the beach ball would explode. You know why? Because on the inside there's a pressure that's a little bit more than atmospheric pressure, and atmospheric pressure is surprisingly high, you know? And so if you took away the pressure on the outside pushing in and just gave that pressure on the inside free rein to win this battle, it would just blow up. And actually, that's what you see on airplanes. Have you ever noticed, like when they bring you bags of chips or something on an airplane, they're inflated? Have you ever noticed that? Look at that next time. Order a bag of chips next time. They're inflated because those bags were sealed at ground level at a higher pressure. They pressurize the cabins of airplanes, but not all the way. So inside an airplane, it's like being at an altitude of like 10,000 feet, I think I've heard. And so they're normal bags of potato chips at sea level, and then you get to this lower outer pressure, and all of a sudden the pressure on the inside of the bag has an advantage, and they puff out. It's the same reason why when you used to put your luggage in a non-pressurized chamber in the airplane, you would get your luggage out and there'd be like shaving cream everywhere because everything that was pressurized would blow up. That, of course, that entire discussion that we just had there has nothing to do with mass. Okay, yeah. Okay, so the beach ball its motion is more affected by air resistance than the bowling ball because it has a smaller mass. The next one is surface area. And I'm going to say in parentheses and shape. The shape matters too, but that's a more complicated thing to talk about. Surface area is sort of easy to talk about. If you decrease the surface area and keep everything else the same, that causes air resistance to affect the motion less. So an example of that, well, imagine dropping a, one of those little green army men with a parachute attached. I'll call it a parachute army man. And at the same time, you drop like a rock or a marble that weighs the same amount. A marble with the same mass. Well, marble is going to hit the ground way before the parachute because parachutes are specifically designed to maximize the surface area and create a shape where you increase air resistance as much as possible. Okay, even though those are the same mass, they won't fall with the same acceleration. And then the last one is speed. If you decrease the speed, that causes a reduced influence of the air resistance on the motion. The example I like for this is if you ever watch like the Tour de France, or like bike racing, not as many people watch it as they used to before before we won't go into all that, but like 10 years ago or whatever, a little more than that, America was like bicycle crazy, not so much anymore. So it's this super long race, like 2,000-mile race. But most of the time, if somebody tries to escape, everyone else can just catch them, and there's not much that happens most of the time. There are two kinds of stages where all of the time gets made up. One is when they're climbing through the Alps and the really high mountains. I'm not talking about those. And the other one is the time trials. And the time trials are where you don't get to ride with other people and take advantage of drafting behind people. You just go out by yourself, one by one, and they time you, and then they compare the times. Okay, and those are where like the person who's going to win the Tour de France wins it on those time trials and in the mountain races. But there are two kinds of time trials they do. The first one is on the flats, like in the cities. So for example, so here's what they look like when they're doing these time trials in the cities. They wear these crazy long helmets. Ooh, that looks like an elf hat. and they wear like sunglasses that are all aerodynamic. Their bikes are like this. They okay, so let's just call it that. Okay, that's what they look like on their time trial bikes. And they're wearing suits that are like rubberized, and their bikes, everything, they're so careful about aerodynamics on their bikes for these time trials that they make all the cables that control the brakes and stuff run through the bicycle because they don't want the air resistance of the cable flap. It doesn't even flap. It's like, it's a steel cable, but they don't want it hitting the wind because it messes up the air, it causes air resistance, you know. Their shoes are all like, they have a rubber sheath over their shoes. Just everything. It's like, they look like robots, you know. They're so this is a flat time trial. And then the other type is they do time trials up a mountain. So even though they're going up a mountain, they do it one by one and they just time them. And going up the mountains aren't really that steep, but they're on bikes that look just like, I mean, they look like 10 speeds or whatever. They look like fast bikes, but they don't look like they were designed by NASA anymore. They just look like what you think of as a bicycle. And most of the time they're riding, they have their hands up. They have their hands up on the tops of the handlebars. They're wearing just regular helmets. They look like helmets you could buy at, you know, whatever, Dick's Sporting Goods or whatever. Suits that they're wearing, they're not even zipped up in front, just trying to stay cool, and they have them zipped down so they're, you know, not getting too hot. So what's the difference here? This is a mountain time trial. These are the same people doing the exact same thing, but the difference is when they're riding on the flats, these guys are riding 35 miles per hour. And when they're riding up a mountain, they're riding less than 20 miles per hour. And that difference in speed is enough that, in this case, aerodynamics is the #1 factor in determining how fast they go. And in this case, aerodynamics is almost not a concern. It's way, way down in the list of concerns. And that's just because of the speed. There's a high dependence on speed for air resistance. And in fact, like if you look at an equation of calculating the air resistance force, speed is squared in the equation. Everything else is you know, linear to the first power, and that's why there's such a big effect. Okay. So we put all this together. What are some things that, yes? Yes, that's right. That's also why when you know, shuttles re-enter the atmosphere, there's this risk of things breaking off of them and the heat melting things. And it's not because our air is, I mean, it's the same atmosphere as here. It's not like they're dealing with extra atmosphere. It's just they're going so fast when they hit the atmosphere, you know, that the effect of air resistance is dangerous, you know. Okay, so here are some cases where free fall would be, assuming something's in free fall would be a good approximation, and somewhere would be a bad approximation. So free fall approximation would be good, and here somewhere it would be bad. It's a good approximation in the shot put, that is in track, where, like if you're watching the Olympics, it's like 300-pound people throwing this steel 16-pound ball. It's relatively compact. It doesn't have a very big surface area. It's very heavy. It has a big mass. And it doesn't ever get going very fast. They throw it 70 feet or something, which is amazing, but it's, compared to the speed of a car or something, it never gets going. I guess it's probably going 30 miles per hour or something, And so if you used a free fall approximation to try to predict the path of a shot after somebody threw it, and you assumed there was no air resistance, you'd get great approximations. And another one where you'd get good approximations is like a baseball that you dropped from a height of 1 meter or something. Okay, so a baseball has a smaller surface area. It doesn't have nearly as much mass, but it also doesn't get going nearly as fast if you drop it from this high. And so in the time it falls 1 meter, it doesn't get going fast enough for air resistance to have a big effect. Some things that you don't want to approximate as free fall would be like any kind of motion of like feathers or pieces of paper. Even if they're going really slowly, they just have so much surface area that there's almost never a time that their motion would be approximated well by air resistance. And then just to make this one last point, it would also be a bad, so you get good results by predicting what a baseball is going to do if you drop it from a meter in the air, but you get bad predictions if you're trying to predict what a baseball would do after it gets hit by, like on a home run, a ball that's hit really hard, And that's just because, it's exactly the same thing. It still has the same mass, the same surface area, but when it's dropped, it never gets going very fast. When it leaves a bat at 120 miles an hour or something, it's going fast enough that air resistance has a huge effect on its motion. Okay. If you use the free fall approximation, then you always know the acceleration, whether the thing's going up or down. You always know the object's acceleration. It's 9.81 meters per second squared directed down. Okay, so that makes sense when an object is dropping down, right? It's on its way down. But what about when an object is in projectile motion, you shoot it straight up? On the way up, is it acceleration down, or does it switch to up, or how does that work? The acceleration stays the same. And that can be a tricky thing to wrap your head around, because I think really the heart of it is like acceleration is a hard thing to imagine, and so you start mixing it up with velocity in your head, which is easier to imagine. But remember it this way. When an object, and we talked about this last class, if you throw an object up into the air while it's going up, is it speeding up or slowing down? Slowing down. And is its velocity up or down? Up when it's on the way up. So which way does its acceleration have to be? Down. And then when it's on the way down, is its velocity up or down? Down. Is it speeding up or slowing down? Speeding up, and so its acceleration in that case has to be down also. So its acceleration, no matter what the thing is doing, is downward at 9.81 meters per second squared. Okay, so I thought we were going to get to some problems today, but we're not. So I guess you can look ahead and try to work through some of those problems, or you can just wait until Monday if you want. Okay, have a good weekend.